the final form I want to achieve is certain, because this is cosine and sine. I want to combine the two terms into the single sine or cosine. And here I pick the cosine. Okay, I want to get this one. So basically here I try to rearrange the terms. Is this? I simply R, and this will be R and minus sigma x minus sigma y divided by 2, and sine 2 theta plus R tau xy cosine 2 theta. Okay, so let me get this one. So which means this one will be equal to cosine beta. This one here I have a typo. I think here is, I forgot the minus here. Okay. So here for this one, I make the whole things. So this is sine beta. So basically here, cosine beta, cosine 2 theta plus sine 2 theta, sine beta basically is this one. So we make up this one. So for this triangle, we can utilize is this. This is beta. And on this triangle, we have cosine beta is like this, so this is the R, and the cosine beta, so this is tau xy. And this is Q minus sigma x minus sigma y. So with these things, we'll be able to calculate. And so for example, again, you look at this. This is a cosine functions, and this is our tau x prime y prime, which is a function of theta. So from this equation, you can see that very clearly, the maximum value of the tau is R, the minimum value of tau is minus R, because the maximum and minimum value of cosine is 1 or plus minus 1. Okay, and in a similar way, we can determine, so when theta equals to beta over 2, then that corresponding to maximum, right? Can see? And here, what is the beta over 2? That is beta, looking from here, is tangent beta equal to this term divided by this term. So basically is arctangent minus of what we have here. Like this. Are we good? Okay. And so that is the give you the information. And so from here we can do the calculation here. Using the same example, and then let me utilize the information here. So on the same example, we can see the maximum minimum equal to R equal to 5, and tau minimum will be equal to minus R equal to minus 5, and theta s equal to how much? 1/2 arctangent inverse minus the difference 10 minus 4 equal to 6. 6 by 2 equal to 3. And then divide by tau equal to 4. Anyone can do the calculations right now? Anyone? Do you have any calculators?
Negative 18.
Yeah, negative 18.4.
45 degrees, about. Negative 18, negative 17.
Negative 18.
Then my calculation, this should be 26, sorry. Okay, sorry, correct this number, please.
For the T min, shouldn't that be negative 5?
Oh, yes, negative 5. Good. So, again, so right now for this one, hopefully you have enough space, but here, let me keep drawing on this diagram here. So that means in the negative 18.5, so in our sign convention, negative is go clockwise. Okay, good. And then in these new orientations, this is our new X prime corresponding to the maximum shear stress. So here we know that in the maximum is R, and so in this way again we come up with the issue is we don't know how to map the information onto here. So maybe likely if you like you can do the calculation one more time, say using the 18.5 degrees, you introduce into this equation, we do the calculation quickly, minus 10 minus 4 times sine and 37 degrees plus 4 times cosine 37 degrees. To do this calculation is how much? Minus 5 times 37. So this would be minus 4 plus this one. No. What is this? Should be negative. Oh, yes, and you can see I made a mistake. For sign convention, this represent is negative, so I should put a negative here, right? So kind of easily make mistake. Okay, so here should be equal to minus 3 times that is 5. The value is 5. Okay, so that means in this new orientation, what is the direction of the string? Here, in this way, or in this way? We got a positive 5. Do you remember our sign convention? Our sign convention for string, this is positive. So now in the new orientation, we got 5. So that is in this orientation. Okay? So this value is 5. Okay? And now in the principle, in the shearing, in this orientation, we can calculate, for example, sigma x prime. 18, sorry, here is minus 18 again. minus 18.5 degrees. We can do the calculation one more time. So we plug into this calculation, then that'll be how much? Sigma plus sigma y, and 10 plus 4, that's a 7, plus, this is 10 minus 4 times cosine minus 37 degrees plus tau equal to 4 times sine 30 minus 37. Okay, so this one will be equal to 7 plus 3 times 4 minus 4 times 5. So this is 7. Okay, so this is 7. So that means the normal stress in the x prime direction is 7. So that is 7 here. Okay, and again, we can calculate sigma y prime minus 18.5 degrees, and we can repeat the calculations. I can tell you the number is 7. So here is 7. So that will be the distribution of the stress components in this orientation. Okay. And here, again, let me summarize. In 26.5 degrees, that is called the principal orientations or principal directions, in which the normal stress is either maximum or the minimum, and no shin stress. Then in the other direction, that is where the maximum shin stress occurred, and that is 7, that's a 5 I calculated. But the normal stress won't disappear in this orientation. Yes?
When you combine those two, 7, that's 14, and then 2 plus 12 is 14, is it always going to work out like that, or is that just coincidence?
You always ask good questions today. Yes.
We got to make up this semester.
And let me give you he asked a question that comes to a very important property about the transformation of the stress. Really doesn't matter about which orientation we rotate. For example, here is the, before we rotate, this is the sigma x. This is sigma y. Sigma x plus sigma y will be always equal to sigma x prime plus sigma y prime. This is the, we call the invariance property. This is a guaranteed truth. Okay, so that is come to the answer to your questions. And again, really doesn't matter in which orientations, the summation of the normal stress components must be equal to the given one.
If they don't equal, then you get problem.
Yes, if that is not equal, then that means your calculation is have something wrong there. Okay, so this provides you the, if you like, you can write it down as the properties. For the second important property is this. This is our theta p, and this is our theta s. The difference between theta p and theta s is always 45 degrees. Always 45 degrees, and that is guaranteed. And that is the properties, and that's one of the good properties of here. And exactly 45 degrees. Okay, if you look at the two triangles here, if you look at the two triangles here carefully, you write it down the two triangles, and you can see the difference between alpha and the beta actually is 45 degrees. Okay, that is due to the property of the trigonometry. And again, the 45 degrees can be explained by using the information. And again, for here, I can say the alpha minus beta equal to 45 degrees. Okay, so somehow here we have a negative value, so alpha intrinsically is a negative value here. Okay. So with those information, I think I have given you much more information in today's lectures, not only to show you the principal stresses and principal orientation, but also the orientation in which the maximum stress occurs. In addition, I show you how to correctly represent the distribution of the stress in the oriented stress element, which is very important. If you only do the calculation, you wouldn't be able to display. For example, that would be on our test. Then you will only get a partial point. So how to correctly draw your result in the good direction, in the correct direction until we